ready? Caitlin, are you ready?
Yeah. What is that? It's huge.
Let's all bring it down. Let's all bring it down. Okay, so we're going to get to the lab today, but we really have to do a pre-lab, and this one is actually more challenging than, sorry, that's right.
So when are we going to the
This one is a little bit more challenging than some of the other labs we've done. So the pre-lab is really kind of hard. I want you to really kind of focus on. Okay. So this is where we were the other day. Okay. This is where we were the other day, and we had our block. Okay. And what we're going to do is we're going to try to pull it, but I'm pulling it because you can see that the string is tight. Yes, but it's not going anywhere. Is it accelerating?
No.
No. What does that tell you about the forces? They are balanced. Now, whether I do it this way or this way, it doesn't matter. The forces are still balanced. Okay. So we're going to take the training wheels off here, and I'm going to draw this, and we're going to name it a little bit differently. So here's the block. George, what does the block weigh?
0.4 newtons. 4 kilograms. 4 newtons. No, 4 newtons. 4 newtons.
Are you sure? This is one thing that I want you to just remember and internalize and be part of the way that you understand the world around you. Okay? As we check up on the front board, the mass is the amount of particles. It's also the resistance to change in motion of the object. The mass is measured in kilograms. The weight is measured in newtons. It's just like pounds. Remember, it's just like pounds. It's just like pounds. There's about 5 newtons in every 1 pound. Okay? So if you weighed 100 pounds, you would weigh about 500 newtons. Okay? All right? And then we have, on Earth, we have a quantity that relates these two. We call it the gravitational field strength. Okay? It's baby G, and it's 10, and its units are newtons per kilogram. Okay? So these three are related through a lab that you did. Do not forget this lab, where you took different masses, measured in kilograms, you measured their weight in newtons. This is a linear relationship. Does this seem vaguely familiar? Okay. And what was the slope of this line? 10 what?
Newtons per kilogram.
That's the whole point. The slope of this line was 10 newtons per kilogram. So when you want to solve for the weight of an object, right? If this is y equals mx plus b, the slope was the gravitational field strength. Okay? So the weight, to find the weight, you take the gravitational field strength times the mass. So that's how we know this block weighs 4 newtons, because it's 10 newtons per 1 kilogram times 0.4 kilograms. Okay? If you could travel to the moon, for example, the mass doesn't change, it's the amount of particles in the object. Okay? If you were to go to interplanetary space, the mass doesn't change, but the weight is determined by the gravitational field strength. If you go to college, you take physics in college, they're just going to call that the gravity value. I don't think that that's actually very helpful to call it the gravity, because I don't know what a gravity is, right? It's the gravitational field strength.
It's just the gravity.
It's just the gravity.
Yeah, like.
But when you say that, do you mean the field strength, or do you mean the free fall acceleration, or do you mean the force? Like, which are you talking
The
about?
force of gravity.
The force of gravity would be the weight, not the gravitational field strength.
But the force is called gravity. The force that pulls you down is not your weight. The force is the gravity acting upon you.
The force is the gravity.
Hey, I didn't come up with gravity. Science did, so.
All right.
Yeah, was it Newton? Yeah. Tesla?
Fine. So, we have our block.
No.
All right, you guys ready? So, this force diagram you already have in your book, okay? But I'm going to use some different labels this time. When I say we're going to take the training wheels off, are we ready to move to using nicknames exclusively?
Yes. Please.
So, that is the string pulling it to the right. What do we call that?
Tension.
You can actually call it the applied force, actually, but we're going to call it the tension because it's a string. But we're applying the force with the sensor on the string, so I'm with
If
you.
you just have four string, would you get one down?
No, that's right. What is the F little sub n?
Natural, normal force.
The normal force. Natural.
I don't know what
Okay. What is the little f?
Friction.
That's the frictional force. And now, this one is a little challenging. So, M is the mass, and G is the gravitational field strength. It's the baby G value. So, if you want to calculate the gravitational force, the weight on an object, you need the mass and the gravitational
So is
field
that what we
strength.
label it? Or do we label
You can do it that way, or you can do it in F sub G. The difference in this is, you can do this. There's a slight difference here that if you're not paying attention, might be hard for you. This is F with a little subscript N. This is F with a little subscript T. This is F with a little subscript F. This is F with a little subscript G, but this is M times G. You with me on that?
Yeah.
One of the kids in my last hour said, "Oh, is that for milligrams?" I'm like, "You're out. That's it. You're done. That's it. If that's what you think, you have not been paying attention for about 3 months. You are out." Okay.
I mean, at least you can like read.
No. There's no at least. There's no at least on this one.
Normal.
That's what we call it.
I mean, he's giving it a thought.
Let's try it.
Yeah.
Listen, you can try your best all you want. If it's still garbage, it's still garbage.
I'm sorry.
It's a math times gravity.
Got you going. Yeah.
So that is the force sensor. So in the lab, you are actually going to be pulling on this with the force sensor. So we're going to be measuring the tension directly using the force sensor, which is a cool thing to do. Sound good?
So we're,
All right?
we can't just figure it out.
Well, no, because we're actually trying to figure out what factors affect the frictional force. So to understand how to get the frictional force, you would need the tension, and we're going to use the force sensor to get the tension.
Isn't there like, oh, okay.
Isn't there an equation to relate it? So that's
No, I was saying something else, but I think that's what the lab is.
That is what the lab is, yes. Okay, you ready? So, here's the question. Okay. So, given this situation, and you know, I could do it with this spring scale, right? If I just pull on this, I'm going to pull just until it starts moving, and you can see it takes about 1 Newton. Actually, it takes about a half a Newton because this is not exactly 0, but we'll let it go.
There's 5 things that affect.
I don't know. There's a bunch. Well, we're gonna brainstorm them right now. So, I would like to know, looking at the situation the way we do it, the way we did it here, knowing that we're gonna pull with the string, and if we could measure the string force, we can understand how much friction there is. What are some factors that we could change that you think might affect the friction?
Mass.
The mass of my object.
Yep.
Okay. Seems very reasonable.
What about the surface?
Yeah, like maybe the thickness or the amount of.
The roughness?
The roughness, exactly. Thank you.
You're
How
welcome.
about the textures of the two surfaces?
Yes, texture.
Sure, that works too. I like roughness better.
Okay. Technical physics term, the roughness.
Isn't
Okay.
there a coefficient?
Thickness of the string.
Okay, so it doesn't.
The thickness of the string?
Yeah.
So we're just gonna use whatever string
Okay.
because we're gonna measure the tension. I don't actually, that's a great question. Does the thickness of the string change the tension in any way? But regardless of whatever string we're using, we're gonna use it to pull. So I wanna know what affects the friction between the two surfaces. Okay?
Gravitational field strength?
Sure, I mean, we could take a field trip.
A what?
Field trip.
It's a space.
Planetarium?
No,
Oh,
I think that's.
the gravitational field strength. If we did this on the moon, do you think there might be less friction?
for sure.
There might be.
But I think that's because the weight.
We're scientists, we have to test it out.
Oh yeah, we have like.
I know a guy.
We can like simulate like what would happen on the moon.
Zero gravity.
Like we
No,
can,
I know a
we
guy.
can have like all like the outer space stuff and pretend like we're on the moon.
What else?
How the star moves through the sky, the friction of it.
How else? What else might you change
Outer.
that might affect
Outer?
the gravitational or the frictional force?
Like outer?
Something else.
Yeah, you're so
Let's
funny.
say outer.
For what? Where?
I said outer space.
Something else?
Outer.
My God.
Gentlemen,
Is that not how it sounds?
No, he says outer.
gentlemen, focus please. What else might you change that might affect the frictional force?
How fast, maybe? Like in what accelerate or
Well, so I like both of these things. The problem is that we need to keep the forces balanced in order for the force we're pulling with to equal the frictional force. So if we accelerate it, that won't be true, right? And right now, we're not even going to move it at all because we're just trying to keep the forces balanced when the acceleration is zero. So I like where you're coming from. Something else.
More like over 30.
Would that create more friction?
Like if you were pushing it from behind instead of pulling it?
Or maybe like a fan almost like pushing it or something like that.
I actually think that the friction is just a function of the way the two surfaces interact, so I'm going to think probably not.
Okay.
What about the material that the string is made of? Like, it
You know,
looks
that's
like
what
a
she
bungee.
said too,
But what
but,
about the material that the block is made of?
well,
That's the texture.
we're just going to use the string to pull.
Okay.
Yeah, we're just going to use the string to pull. And the material the block is made out of, that will change the textures. Annabelle, can you shut the door, please? What else? Come on. What else? What are we missing here?
The normal force?
So, how do you...
Just grab, yeah, I don't know.
No. So,
No, that's.
I'm going to tell you what Brendan said because it actually makes a lot of sense. Okay? Marge, can you come up here and be the helper real fast? So right now, one of the things that we know, okay, is it takes about a half a Newton to get this thing to go. If I put this block on here, do you think it's going to increase, decrease, or is the friction going to stay the same?
Increase. But that's because of the mass.
Sure. Is it take more force to get it to go?
Yeah.
Okay, now watch what happens here, okay? In essence, what we did by increasing the mass, okay, stay because you're going to be needing about 10 seconds. By increasing the mass, what happened? What increased also? The normal force increased, which then somehow increased the frictional force. But what Mars is going to do is she's just going to push down on the middle of those, okay? Just a little bit. Perfect. And now I can get them to go, but does it take more force?
Yeah.
Thank you, Mars. Very good. So what she did here, and this is really interesting, is she said, look, I'm just going to add an extra down force here. But there was no acceleration in the up and down direction, right? So what happened was then the normal force increased also. So this isn't, I mean, what we did here is we pushed down, right? But what I'm going to tell you is that all three of these things are a change in the normal force. All three of those things are a change in the normal force. And you can change them in one of three ways. You could just change the mass of your object. You could push down on the object. You could change the gravitational field strength. All that changes the down and up forces. And what we're noticing is that if you increase the normal force, you get an increase in the friction. I would like to know, actually, what kind of relationship exists there. Like if you double the normal force,
Don't you need the normal force to calculate the frictional force?
you do. We're going to measure it, though, to figure out what that relationship actually is. Like, what is it linear? Right? If you double the normal, do you get twice the friction? Or is it quadratic? If you double the normal, do you get 4 times as much friction? Or what if it's square root? If you double the normal force, you only get like 1.4 times the friction.